And if you take any arbitrary data, you try to find a wave that's actually sit right on the x-axis and symmetric with respect to x-axis, the probability is probably 0. You will never find that. So if we cannot find that, my question is that can we move the wave down to the x-axis? Yeah. So that's the way of how to make all this wave. You see, this wave you sit right above the 0 axis. This wave is sit asymmetric with respect to the 0 axis. Now, the next step is to move all the wave to the 0 axis, the x-axis. The way I did that is a very, very simple way, extremely simple way. What I did was that I located all the extremas including maximum as well as minimums. And then I divide the extremas in 2 different groups. The first group is all the maximum. Maximum here, maximum, all the maximums. And then I will connect all the maximum with one continuous line. This continuous line is a cubic spline. Yeah. There are many different splines. Yeah. If you go read the book, you'll find that there are different splines. The spline is typically a polynomial function or any form of function. Here, I choose the cubic spline. And this cubic spline is also a natural spline. I make all the extrema place derivative equal to 0. So if you take all this, then what you have is you have a continuous line connecting all the maximum. And you can do the same thing to connect all the minimums. So this maximum minimum lines form 2 envelopes that encompass all your data inside these 2 lines. You notice that the maximum line and the minimum envelope, they are totally not symmetric, unsymmetric. Okay. But at each point, however, you can actually look for the mean, the average value, the mean of the upper and lower line. And this upper and lower line, because this is a continuous line, this is a continuous line, so we can actually get a continuous average of the upper and the lower envelope. Okay. Once we get the continuous upper and lower mean of the upper and lower envelope, now this line actually divide the the height in 2 parts. And if I now move my x-axis to this red line, then the wave actually is being moved down to the x-axis. Now, how do I move this to the 0 line? That's very simple. You take the difference between this line and that, your data with the mean average. And if you do that, what you got is that you have the original data is in this light red line. And now, after you take the difference between your data and the mean, you successfully move all this wave down to the x-axis, and you move this wave up 0 axis, and even this wave is totally asymmetric. Now you move up, and it becomes much more symmetric. And if the construction is correct, one consequence is that all the maximum of this blue line should be positive, because you see this line divide the maximum and the minimum envelope. All the maximum is on one side and all the minimum is on the other side. And if I move the x-axis to this line, maximum should be all positive, minimum should be all negative. And if that's the case, then I'm very happy. I reach my objective. Now you see, all the maximum are indeed positive, all the minimum indeed are negative. Even this wave get moved up, that wave get moved down, and you are very happy until you come to this point. This point is an anomaly. This point is that this is minimum, but minimum still above 0. Why this becomes so? This is because the original point is not an extrema, not a maximum, but an inflection point. That is, it's changed from concave upward to concave downward. Okay, its derivative is 0, but the second derivative is also 0. So we cannot tolerate that, because if we have that, and this particular wave will be the time kc as we have it. This minimum is above 0. So what do? We will then, this point, the reason it becomes that is if we look at this. Here, this is the point. This is not extrema in the rectangular coordinate. But if you move the coordinate to this line, then this becomes extrema. It's because of the curved linear coordinate that we introduce. Now, if we notice this anomaly, so we will then do it another time. Yeah, we will take the maximum and take the minimum again to plot the envelope. Now you notice this envelope, this upper and lower envelope, it's much more symmetric compared to the previous one. The only part that's not symmetric is in this area. This area is where it violates what we originally started with. So with this, then we can again draw a average line. This average line is still not 0, not flat. Now, this is not flat, but compared to the previous mean, this is much more manageable. But then, since we have to do this, and we'll do this again, if we take the difference, it becomes that. And that's still not good. We'll do it another time. Look at this envelope. It's getting more and more symmetric. Okay? And we can do this any number of times. This is the third time, fourth time, and we can keep on doing this. The way is that your x minus mean 1, the first mean, that equal to h1. We take h1 as our data minus the second mean, h2. We keep on doing this until the kth time. Okay? And by the kth time, how do we choose kth time? There are many ways to tell us when to stop. Okay? The most popular way is doing this way. That is a Cauchy type of convergence criteria. If I take the kth time and compare to k minus 1 time, and if the difference is so small, I don't care, then I stop. So you can choose a criteria, and this criteria is chosen by us. Okay. So at the very beginning, I told you that the science and engineering is for approximation. So for this is the tolerance that limit of the tolerance. And if we decide that's it, then that will be the the final HK, and that HK we call it the C1, and this HK has all the maximum positive, all the minimum negative, and the envelope is very, very symmetric. When I say very, very symmetric, I mean it satisfies the criteria that I imposed at the beginning. And this function is very interesting. This function has two interesting properties. The first interesting property is that the number of extremas, maximum and minimum, exactly equal the number of zero crossing. The number of zero crossing and the number of extrema equals. But at most, they differ by 1. That depends upon whether the last one is extrema or not. If it is, then it maybe have 1 more. And if it's not, then the zero crossing may be 1 more. But it's no more difference, no more than 1. That means from each maximum you want to go to minimum, you have to cross 0. From each minimum you go to the maximum, you have to cross 0. And at the beginning, our data does not have this property. Yeah. And this property in the 1940s, S.O. Rice studied the random statistics of noise. And he published a series of 6 very famous papers on the statistical property of noise. He actually worked for Bell Lab, and the reason that he studied noise is that the telephone always has a lot of noise. And Bell Lab says, okay, go study this and tell me why we have noise. So he studied the noise rather than tell them why we have noise. But he studied the statistical property of noise very well. And that laid the foundation of the application of statistics. Later, all the statistics that I use in study ocean waves and other people study ocean waves primarily borrow his data and move that to the wave. So we have this, and in his study, what he finds is that if the noise is Gaussian, and if in the Gaussian noise, and if the extrema number equal to 0 crossing, then this has to be narrow band. That means the frequency has to be very, very concentrated in just one single frequency. Yeah. But when we look at this wave, this signal, we find this signal is not narrow band at all. The reason is that you can see that we have very large wave, we have a very small wave, we have very large period, and then we have a very small period. So for a wave, for a signal that is wave, has the same number of extrema and 0 crossing, and it's also symmetric with it, but it's not narrow band. This kind of data, this kind of function I have never seen. And I don't know how to code this data, so I give this data a name. I define this as intrinsic mode function. Yeah. Intrinsic mode function is very simple, and the definition is that any function having the same number of 0 crossing and extremas, and the envelope defined by the maximum and minimum are also symmetric. In other words, you take the difference, it will be near 0 to a tolerable region, tolerable number. So that function I call the intrinsic mode function. This intrinsic mode function is very different from Fourier function. Yeah. Fourier function is a mode, but it's not intrinsic to the data. Fourier mode is a mathematical term, the sign. Okay, this is not a mathematical term. This function is derived from the data. So the intrinsic mode function will enjoy good Hilbert transformation. Now, once you take that away, what do you have? You have a residual. And what is the residual? If you take C1 away, the residual actually is this. See, this is the last. I keep pushing the mean. I keep pushing the mean. Okay, this is the sum of all the residuals, and that's the total residual. That this line. This residual has a very interesting property again. Now notice this residual. It will go through every oscillation and bisect all the oscillations, no matter how small. You see, even this line will go through this and bisect that, and this small will bisect that. So in a way, I find a line with this very simple method. I find a line. This line will go through the original data and bisect every wave, large and small. Yeah. So, but is this a running mean? It's not, because you see, if you take a running mean, you have to say, I take a section of data, I average it. I've never averaged anything. So this average is achieved not by taking the data and average it, but this mean is taken by take upper and lower envelope and take the mean of the envelope. So I did not invoke any time scale to achieve this mean. And that is the advantage that I enjoy. That if you invoke any time scale to achieve a mean, then you have to make assumption of what is the time scale involved. And that you most likely you'll be restrict yourself to stationary processes. Yeah. Now here, I did not invoke any time constant. So this mean is an effective mean, but this mean is not involve any time. This mean only involve the envelope. Yeah. And it works only for one point. It's here. The next point it's changed. Yeah. So this is a much better mean than the running mean, I think. Now, you see, if I take away the first component, what's left is actually this mean. This mean still contains a lot of information. And that what the information contains the big wave. All I took away are all the small deviation. I did not take away the large deviation. The large deviation becomes my mean. So, because of that, that mean is that red line. I take that red line as my data. I can do the same thing, and I get another mean. That mean still may not be flat, totally zero. Then I can keep on doing this until the nth step. The nth step, I can stop. What is the property of the nth step? The nth step is that there's there's only one extrema. If there are two extrema, then I can draw the envelope. If there's only one extrema, then one point does not define any curve. So I stopped. Okay. I stopped here when my residual is only have one extrema. And once I achieve that, then I sum this all up. What we got is that you see this R here, this R here, this cancel. This R here, this will be another R cancel. All the R's, all the residual cancel. So we have on this side, on the left side, x minus summation Cj equals to only one left is Rn. It's the last residual. Okay. So this summation Cj, each of this Cj is an intrinsic mode function. So in this way, I successfully reduce my data as a sum of Cj, sum of intrinsic mode function. Many incidents, this Rn becomes either zero or a constant, depends upon your data. Yeah. Most of the cases, it will be a monotonic function. Yeah. If we have a monotonic function or whatever, this term is usually treated as the trend of the data. Yeah. This trend, we will talk about this in the class, of course, very in much more detail. This trend is what we call the overall trend. Trend is much more complicated than just an overall trend. When we come to that, we will discuss it. Okay. So in this way, we successfully decompose the data into different intrinsic mode function. And see, as I said, this is the first mean, the first mean compared to the first time we get a mean. It's very different. And what's the difference? The difference is that when I first get the first time I get the mean, on this side they are very, very similar, and I actually move it very small. But each time I do it, I move the mean curve slightly. Each time I move it slightly. And in such a way that originally I missed this data, and eventually I push it up and go through that oscillation. And I originally missed this, eventually I push it up and get that. So the repeat, the iteration of the average process pushed my x-axis from this point eventually to that point. Yeah, to that line. Now, having got this, this is the component. The first one, if you go through the second one, the third one eventually becomes almost constant. Yeah. So this scale is the smallest wave, and then the longest. This is the shortest wave, the longer wave, and the even longer, and eventually becomes almost flat. Yeah. This is the decomposition, and once we have the decomposition, then I can do it. I can compute the instantaneous frequency. The instantaneous frequency is that is defined this way. I have my intrinsic mode function. I will make a Hilbert transformation, a Fourier transformation of the the intrinsic mode function. The Fourier transformation can be written in this form because this is written as A E I theta. The Fourier transformation is multiply I E I minus omega t. So it's a theta minus omega t. I don't care what the spectrum looks like. I only ask a question: what is the major contribution to this W omega? And that can be obtained by the method called the stationary phase. The maximum contribution that you have to this value is when the phase becomes stationary. And you take a derivative of phase, set that equal to 0, so d theta dt equal to omega. This, in other words, define d theta dt as omega. Mathematically, is to the stationary phase approximation. Yeah. And physically, it's the classical wave definition. The classical wave theory, the definition of frequency is that if you have a phase function, the time derivative of the phase is a frequency. The spatial derivative of the phase is wave number. And this frequency, this will be a crucial concept that we introduce here. Instantaneous frequency is not new. Anybody study like electric engineer knows that there's a phase and time derivative of phase is frequency. Yeah. But unfortunately, most of the time you're dealing with a very simple function, sine, cosine, or whatever function. For arbitrary function, you think you can define time derivative of phase as frequency. But if the function is not intrinsic mode function, that definition does not make sense. So in the past, even every person, if they want to use that, they usually define define a phase as a gradually changing function. They never been able to do arbitrary function. Here, we find a way to do arbitrary function. Any data you give me, I will decompose it. Once it becomes the intrinsic mode function, then I can use Hilbert transformation to get a phase. And the phase, time derivative of the phase, give me frequency. That frequency is very different from the physics book give us omega equals 1 over t. Physics book always define frequency as inverse of the period. Okay. The inverse of period sounds great, it's good, but it only makes sense for sine waves. Constant amplitude, constant frequency waves. Yeah. And for general wave, we cannot define frequency as 1 over t because the period keep changing, and not only period changing, this is extremely crude. If you define frequency as 1 over t, it's like we define velocity as distance divided by time. Yeah. Physically, it's right. Velocity is distance divided by time. But then you have to tell me how long a distance, how long a time. See, if I drive from here to Taipei, it took, say, an hour. All right, the distance is, say, 40 kilometers. So my speed will be 40 kilometers per hour. True, but that's the average value. Very crude mean. But on the way, my velocity keeps changing. If there's a traffic jam, I slow down. If there's no traffic jam, I can speed up to say like 100 kilometers per second, per minute, per hour, sorry. So velocity equal to distance divided time is mean velocity. So Newton told us that the velocity should be dx dt. Yeah? And the frequency is 1 over period is also a mean frequency. That's a very crude definition. The velocity should give us, the frequency should be d theta dt. For any arbitrary function, we should define that way. And that is one way, using this simple approach, we eventually define frequency truthfully. And we will get into this in the course. Now, having the combination of Hilbert spectral analysis and empirical decomposition is designated as HHT by NASA. This is a little bit history. I find this method through correction of a mistake. And even after I find this method, I still find this method so simple. I don't feel very proud. I try to hide it. But I did solve a few problems. So when I showed this to my PhD advisor, and he asked me, so how did you get the answer? I said, well, you don't want to know. This is very simple. But then he told me, he said, listen, if you don't tell me the answer, the method, I will not discuss with you the results. So he asked me what's the method. So I tried to hide it because, as I said, I'm not proud of this simple method. And I give up the method little by little. After 2 hours, then he told me, he said, listen, he said, I know you wrote a lot of paper, but nobody will remember your paper in a few years. But if you write this method up, there's a chance that people may remember you a little bit longer. That's kind of encouragement that I have never got. So I said, all right, I will go back and write this method up. But when I was leaving his room, I walked almost to the door. Then he says, Norton, another advice. I said, what's your advice? He said, don't try to prove it. Prove this is not easy. Now, it's 10 years later, I still haven't proved it. And I'm now invoke the highest power of mathematicians that I can find. And now I have invited Professor Ingrid Dobischi. Anybody has played wavelet will know her name. Ingrid Dobischi is the mother of wavelet. It's not mother wavelet, mother of wavelet. Without him, there would be no wavelet as we know it today. Okay, I got her to join me, so we have a study grant. We'll study the mathematical foundation, but I don't think we can get there. I still don't think we can get there. In addition to her, I also went to Caltech, and I got Professor Thomas Ho. Thomas Ho is holding the same chair as G.B. Wheaton at the Caltech. He's the director of applied and computational math at Caltech. He's also joined me in trying to find this. So that is another story. So when I got this method, I wrote it up. Then I found this method, it's really very useful. So I went around to give seminars. And one of the places I give seminars was Caltech. And when I give this talk at Caltech, a professor stopped me. He says, after the talk, the professor came to me and says, Norton, have you patented this method? I said, no. How can you patent this? He said, no, listen, you better patent it. So I went back to NASA and talked to the patent lawyer. And patent lawyer immediately decided this is patentable. But then he asked me, he says, have you disclosed this method? I have no inkling of patent. I've never thought of patent. So when he say whether I disclose this, I asked him, what do you mean by disclose? He said, well, disclose means you have speak to the public. about this method? I said, yeah, I did. I give seminars all over the place. So he asked me to write down every seminar I give. And it turns out the first seminar I gave was 11 months ago. Yeah, by then. So the patent lawyer immediately patented. In the United States, you have 1 year of grace period. And that grace period, he immediately filed a patent, and that was able to protect the method for NASA. Yeah. And then NASA, at the beginning, NASA called it empirical mode decomposition and Hilbert spectral analysis. It's a long word. Each time you say that, you after you say it, the people already forgot what you talk about. Most people try to use acronym. And when I was at the Caltech, the professor not only asked me to patent it, he also gave it a name. He said, listen, when you patent it, instead of FFT, you call it HHT. Yeah. So during the process of patent, which is cover about 2 years, I told the patent lawyer the joke of HHT, and NASA lawyer immediately jumped on it. He said, all right, we'll call it HHT. Yeah. So HHT becomes NASA official name. Yeah. And not many people know what HHT is, but NASA's interpretation is the Hilbert-Huang transformation. Okay. And that gives me enormous amount of difficulty. Whenever I talk about HHT, people will always ask me, so what's the H stand for? If the first one is Hilbert, the second one, who's the second one? If the second one is Huang, then which Huang is talk about? If I say that's yours truly, then everybody decide not to listen to me anymore. Says, how can you have such a thick skin to put your name on the method? And I've experienced a lot of embarrassing moments. So finally, I decided to change HHT to a different designation, different from NASA. Notice, Fourier transformation is fast Fourier transformation. The second F is Fourier. The first one is fast. Fast means quick. Okay, so it's adjective, and noun, and transformation. Now this should, if this were Hilbert and Huang, there were two nouns. The couplet, it's not very well matched. And the professor at the Caltech is a Chinese, by the way, and he's very, very well versed in Chinese. I don't think he will have made such a mistake. So I think the first H, the second H should match to be matched Fourier, the name. So the Fourier, this should be Hilbert. The first H should be adjective. So I designated the first H as happy. So now it becomes happy Hilbert transformation. So after I changed the name to happy Hilbert transformation, I have absolutely no difficulty with my audience. Everybody agreed, and everybody happy. Okay. So remember, happy Hilbert transformation versus fast Fourier transformation. Now, since we invoke Fourier, I would better know him. This is Fourier. Fourier is a handsome, a very handsome man. He's a very smart person. He comes from a very humble family. His father is a tailor, sewing clothes for other people. But he's so smart, so from very young, people start to notice him. Even when he's very, very young, he can write a good lecture for other people to read. Yeah. Then later, of course, he's not only good in writing, he's also good at math. In 1807, he solved a problem. The problem is on the propagation of heat in solid body. What he did was that he studied, this was one of the problems posed by French Academy. He says, the problem is if I have two solid bodies of different temperature, and if I put these two bodies together, how the temperature will change between the two solid bodies. You can solve that. Try to solve that. Of course, that's a diffusion equation, but how to solve that diffusion equation? So he come up with the method using Fourier transformation. use a transformation, trigonometry function. Trigonometry function has been used earlier by Euler and by other people, but no one has written a complete theoretical foundation as complete as Fourier. Okay, so after he finished that, and he won the prize. The prize eventually was announced in 1812, grand prize. So he won it. As a young man, he won a Academy Prize. That's a big honor. So he was very happy, and he tried to publish his paper in the French Academy. Now, when he submitted his paper to French Academy for publication, the paper was sent to be reviewed by the greatest mathematician that the French ever produced, Lagrange. Yeah. Lagrange looked at the paper and decided, yeah, we already give you the grand prize. You should be satisfied. And how can you try to publish this paper? This paper is no good. That's Lagrange's conclusion. And his conclusion is that his analysis to integrate them still leaves something to be desired on the score of generality and even rigor. It's not rigorous, not general enough. Why it's not rigorous? Fourier made a very big claim. He said that when I brought the two bodies together, temperature 1, temperature 2, together at the interface, we have a temperature jump, right, from 1 to 2. Fourier said, no problem. If you use trigonometry function, you can integrate it, and at the interface, at the boundary, the value will converge to the mean. Yeah. And Lagrange, and after the mean, you jump to temperature 1 and temperature 2. So this is a discontinuity. Lagrange said, well, listen, you use continuous function, and you try to show me that you can converge to a discontinuous value. You have to prove this. Otherwise, I cannot let you publish because it's not rigorous. How can a continuous function become discontinuous? That's a very legitimate question, especially in the in the 19th century. The mathematics becomes very, very rigorous. It's not just anything work, it will do. Yeah. It's not like in Newton's time that calculus works. That's fine. People later, of course, ask lots of embarrassing questions. So what do you mean by infinitesimal? What's small is infinitesimal? How small is infinitesimal? Yeah. Newton cannot answer that. Nor Leibniz cannot answer that. So they published their paper and say, well, this is an algorithm. Okay, forget about these little questions. So this paper was rejected. Then Fourier says, fine, it's rejected, fine. He went back and be a something like a county administrator. And he did a lot of wonderful work. And he also works as a director of Egyptian Institute. Napoleon has tried to conquer Egypt, and he brought back a lot of artifacts, museum pieces. So he asked Fourier to arrange this, to organize it. And so Fourier studied all these artifacts. And one of the things that the Fourier accomplished during his directorship tenure was to decipher the hieroglyphics, the Egyptian writing. Yeah. Of course, he did not decipher it by himself. Under his direction, Champollion, Francois Champollion, father and son, deciphered that. He made a lot of contribution. Because of his various contribution, he was elected to the Academy of Science, yeah, of French. And at that time, Lagrange died. He was elected to that. And 5 years later, he was appointed the secretary for mathematics and physics section. Secretary means that he run the whole academy of that particular session. So he ran mathematics and physics. He said, all right, now I'm in charge. I think my thesis can be published. So he sent his thesis to be published. The 400-page thesis was published. 15 years later after he first discovered that. And that was what we now read as Fourier transformation. Yeah. The true proof, the true mathematical proof, has to wait until 1935. Yeah. When I studied in graduate school, I studied math. After we went through all the real analysis, went through the measure theory, went through the Lebesgue integral, then we prove Hilbert transformation, the general theory. Yeah. And the general theory statement was a page and a half. They used measure theory and all that to prove the convergence. This work, Fourier's work, is really wonderful, and it's been used for almost 200 years now. 1807 to 2007, 201 years now. It's so great that Lord Kelvin even said that Fourier's work is the greatest mathematical poem. Yeah. To make mathematics as beautiful as a poem, that's unbelievable. Now we have to examine how beautiful it is. Let's see. If I have any function xt, if I give to Fourier, what Fourier will give you? Fourier give you the real part of AJEI omega jt. Yeah. This A is constant, omega is also constant. So what Fourier give you is a whole bunch of sine cosine. Then if you give the same function to me, I will give you the real part of ATEI omega t. That's the difference. The difference is that this A now becomes function of time, omega also becomes function of time. With this, I elaborate the straitjacket of constant amplitude and constant frequency to variable amplitude and variable frequency. Yeah. How important is that? We'll see. If I give you a function like this, this is what we call the chirp. The frequency keeps changing. Yeah. The frequency is very large, frequency is very low and becomes very high. And frequency variation within the function. And actually frequency change from point to point to point, each point frequency change. Yeah. This is very easy to write this equation. You just write it, the omega as function of time. You'll get this function. This kind of function is very common. It's not a function that I, on purpose to find it, try to find the trouble for Fourier. This function is so common like that whenever I talk, my voice is chirp. When the birds sing, the bird's song is chirp. Yeah, the frequency keeps changing. If my frequency will not change, I will never be able to speak. Let me say, I will not be able to speak in a sensible way. The reason I pronounce different words is because the frequency is changing and my amplitude is changing. That modulation gives the sound variation and make the sound meaningful. So changing of frequency is a very common thing in nature. Now, if I give this to Fourier, how will Fourier do? How will Fourier analyze this data? The Fourier analyze this data. This is time. The Fourier I plot time here. This is the frequency. This is energy. The Fourier will give you, as I said, amplitude and frequency are not function of time. So you want to determine the amplitude and the frequency. As far as time is concerned, it's constant. So it's a straight line along here. Yeah. So the only thing that you can vary is in the frequency space here and amplitude. So because this is totally constant, no one plot the Fourier result this way. Only me. Only I plot it this way just to make an illustration. Okay. So the only information you have is a projection of this cylinder to the frequency energy space. That's this curve. So what Fourier tells you is, okay, here you have this frequency and you have many different frequencies. How many frequencies you have? component I have 1024 data points. You have 512 sine functions. You ask them, so which one is this particular frequency? This particular frequency turns out is the mean frequency somewhere here. And then all the others are all sine wave from beginning to end. I don't see that frequency at all. But it's miraculously, if you add this 512 sine wave, you will recover this function perfectly because the Fourier is complete. Yeah. So what that means is that the Fourier, from a mathematical point of view, he can represent a function without any mistake. And that's this. And this function, and you ask them, well, what each of this frequency means? This is never mind. Okay? If you add this, it will be the final answer. Each individual component has absolute no meaning. And where do you see the frequency change? You don't see it. This is all symmetric. And that kind of question lead people to wavelet. Wavelet say, oh, Fourier is no good. We can tell you how the frequency change. This is time, this is frequency. Wavelet give you this kind of change. So that's why wavelet becomes so popular. But wavelet is again an a priori base, the function, and there are lots of problems about leakage and about all the other things, especially when you use continuous wavelet. It's not orthogonal, it's not energy conserving, there's lots of issues. Yeah, you can use discrete, but discrete only have a few frequency. You may find 4 or 5 frequencies. That does not give you a continuous line. So you have to use this overly redundant method to get a pattern. Yeah. For wavelet, if you want to compress image, the discrete wavelet is the wavelet of choice. But if you want to see the meaning, extract feature, continuous wavelet is the choice. But I say continuous wavelet has all this problem. Now we move from continuous wavelet to Hilbert, and that's very clear. This one line. Yeah. The reason that this line is a little bit width is that if I draw one line, you would never be able to see it. So I enlarge it just to show to you. Yeah. So this is the difference. We can faithfully portray the frequency change from time to time, from place to place. That's the difference. And that is also the reason I say that if you try to process data without thinking, using Fourier, you have all these waves. These waves, are they meaningful? Yes, mathematically. This, are they meaningful? Yes, physically. You get the meaning. And that's the difference. And if you look at this and you look at this, when you look at this, I will ask you, so what do you see? You see, I see 500 waves. But how can 500 waves be put back in this? That's not a simple problem. For example, I can use 500 wave to sine wave of the same amplitude and the different frequencies. I can use 500 waves to make a delta function. I can use 500 waves to make a noise. Their spectrum looks identical. So Fourier analysis is incapable of representing any variation in the temporal space. Yeah. And it's even incapable of separate noise from delta function. I will try to show you this. Let me see. I have, in that one, I've added 500 sine waves. Each wave I add, it becomes increasingly moved to a delta function, right? And now if I close, I'll run this again. Notice, the more you add, the delta is narrower, and it eventually becomes almost a delta function. I should probably stop at the last one. However, if I try to use the same delta function, the same sine wave, I add 512, it becomes noise. Both delta function and noise has a white spectrum. The spectrum is flat, but the same amplitude is constant, frequency is different. Okay, so it's all white spectrum. One is delta, one is random noise. What's the difference? The difference is phase. In Fourier spectrum, the phase information is not there. If you do Fourier transformation, the phase is there. Yeah, you can use the imaginary and the and the real, and you can recover the phase. But using Fourier spectral analysis as we know it, derived from Werner crunching theory, the phase information is lost. So it's incapable for us to separate the two. So with that, now we find that the Fourier analysis, as we know it, has really problem. The problem that not tracking the phase is not tracking the time is really a fatal flaw. For example, in this room, if I draw the curtain and the room becomes totally dark, I flip the switch and I generate a spark, a flash, and then I have a zero light and suddenly one light and then come back to zero again. This is delta function. And I give the Fourier gives me 512 waves. And if I ask him what's the physical interpretation of these 500 waves, then he would say that if I have 500 switches, each one switch on and off like a sinusoidal, okay? And if I make a certain arrangement of every one switch at the same phase at the beginning, then I will be able to reconstitute the delta. But that is not possible for two reasons. One is we cannot make a negative brightness. Two is that whenever I switch the wave on, we're actually predetermining when at the beginning the phase is. So it's impossible for you to predetermine when I will turn on the switch. So Fourier has all this problem. So that's why we want to find some method that will actually give us the time component. And this is the method that I try to convey to you. And I have told you that this empirical mode decomposition has certain advantage. Let's see how it works. So we'll come back to this data again. This data, as I told you, it's length of day. If I go through the program I told you, take the maximum minimum and draw the mean, maximum minimum, draw the mean, and eventually you'll get 12 components. Yeah. And each of these components actually are physically meaningful. Yeah. The 12 components, it's a very low number. Remember, I have data. This data is 14,000 data points. And how many Fourier components I will get? If I will use Fourier, I will get 7,000 sinusoidal. Here I only get 12. And imagine, if I have 12 components, I can express this idea as the 7,000 Fourier, then each of these components has to contain a lot of more information. In other words, the information content of this data is extremely high. Now, let's look at this. See this data? This data has a little bump. This data has a general hump. This data, if you expand it out, it has a wave just like this. Turns out this is half monthly period. It's time. That's the rotation of the Earth is influenced by the moon. The moon generates tide. Tide generates friction, and friction slows down the Earth, rotating speed of the Earth. Yeah, and this is monthly time. This is half yearly. This is yearly. This half yearly and yearly is actually the tide caused by the sun. Yeah, it getting close to the sun, far away from the sun. And not only that, you look at this. This little bump within each is actually spring tide and fall tide. Yeah, spring and fall, the tide is much bigger than summer and winter. Yeah, so each year we have two bumps. One for spring, one for summer. And then collectively we have another beat. This other beat has a mean period around 19.5 years. And that is Metonic cycle. This Meton is a Greek astronomer, lived in 200 BC. And he discovered Metonic cycle in 235 BC. He observed the sun and moon at the summer solstice, and he concluded that every 19.5 years, the moon, the phase of the moon and the sun will come back to be exactly when he said. Now we know it does not come back exactly. It comes back within 2 hours. Yeah. His observation is so good. This 19.5 years turns out is very important for people who use lunar calendar. Every 19 years, lunar calendar and solar calendar come back to be matched exact again. Yeah. So, and this, as I say, half year and year. When you look at it yearly, you find that the amplitude is different and the period is also slightly different. And this is what the amplitude as function of time, frequency as a function of time means. Yeah. This function, however, has a very nice property that they are orthogonal. This is a inner product value of component 1 to 2, 2 to 3, 3 to 4, and 11 to 12, all the way. And if you sum up all the off diagonals, so it's Ci times Cj when I does not equal to j, it comes up to be 4%. So for a decomposition in a limited data length, it has achieved this kind of orthogonality. I think it's very, very good. You can try Fourier, and you find that the Fourier may not even be as good as this, depends upon the period you have. Okay? Not only that, if we try to add up all 12 components back, we would recover the data totally. How can we do that? We'll demonstrate. So this is the last component. We add another one, we add another one, we add another one. You see, each one add, I get successively back to the data. And if I add another one, I would add to the annual cycle. The annual cycle, say, if I enlarge a piece here, you will see this is the data, this is my annual cycle. After I add the annual cycle, my curve actually went through each cluster of data in the annual time scale. But I made the important mistake. The annual cycle has a bimodal. I only go through the middle. Yeah, this is because this is spring and fall tides. So fine. We'll add halfly. Once I add halfly, you see I successfully even include that. So each scale you add will actually make the data closer and closer to the original. If you add all 12 together and take the difference between that with the original data, you get a 0 to about 6 plus minus 6. But it's a 10 to the minus 6. So original data is has unit magnitude. Now it's 10 to the minus 6. It's 1 millionth. How come I get this? Because the data I got has a 6 decimal. And this is the round-off error that I made. Yeah. So this is as complete as the computer will allow me to do. And another very interesting thing is that originally, remember, when I do a Hilbert transformation, it looked like this. And I told you this does not have information. But once I decompose it, I take the annual cycle. The annual cycle can be very neatly wound around like this. So out of this mass, I was able to get an annual cycle like this. So that means I'm able to extract information out of this and give you the annual variation. Not only that, if we plot the annual variation, the annual variation is like this. As I said, some are bigger, some are small. Okay, they are symmetric, and you cannot see very clear. So if I draw an envelope on this envelope has high and low spots. Why we have high and why we have low? The high and low means the year is a little bit longer than the other for the whole period. And it turns out that each of these high are the El Nino years. El Nino years are the years when the equatorial water becomes very warm. Yeah. And when you have a very warm equatorial water, the ocean gives more energy, heat energy to the atmosphere. And the atmosphere will move more violently. Yeah. As atmosphere is the outside shell of the Earth. And when the Earth is rotating and atmosphere moves more violently, it will slow down the rotating speed of the Earth, giving the conservation of angular momentum. It's like, for example, a skier. A skier is spinning. With the fastest spinning is to make your body moment of inertia smallest. So you try to stand as straight as you can with your arm all the way to the point. And if in your spin you start to wave your arm, your rotating speed will slow down. Okay, and that's exactly what happened here. Your rotating speed slowed down during the El Nino year. So during the El Nino year, each day is a little bit longer. Yeah, but don't rely that to catch up your homework because the length change is 0.2 of a millisecond. If anybody can count a millisecond, perhaps you'll work. But otherwise, this information is interesting, but to our daily life, it's not quite useful. And if I use the Hilbert transformation to compute the frequency, you will find that this is the monthly, half-monthly period. Half-monthly period is not exact 24 because lunar month is much shorter. Lunar month is 29 days rather than 30, more than 30 days. So it's shorter. And lunar year, the leap year is every year we leap a month rather than a day. Yeah. So in 19 years we have to leap 7 times. Yeah. That's why this is not exact 24. But this is half monthly and this is monthly. And we'll talk about this fluctuation when we come to the instantaneous frequency. And then this is half yearly, this is yearly. So you see, as function of time and frequency, you get every signal, you can see how it varies. Tide is a problem that has been studied longer than Fourier even. Yeah. This is how people do tide. People can predict pi very nicely, years ahead of us. Yeah. How they predict it? They use Fourier. Yeah. Or Fourier, like a Fourier, something like a Fourier. And by the 19th century, using Fourier, of course, is possible, but they don't have such good computation. So what they have is to make a tidal machine. The tidal machine is a wonderful machine. Look at how many gears they have. Yeah. Each gear theoretically represents a Fourier component. Yeah. Not only that, each component are interrelated by the, say you take a side view, you look from this side. This side view is that on the face there are lots of gear. In the back there are gear. And gear after gear, they are all interconnected. Yeah. This is a very, very ingenious machine that once you get in, that you can rotate it and you can predict the time like exactly, almost exactly. Yeah. All of this is based on Fourier. Yeah. Each component is a periodic rotation. It's a circle, has fixed number of gears. Yeah. As a result, many people really believe tide is linear. I maintain tide is not. The tidal frequency, you can compute hundreds and hundreds of terms. Each one you can affix name and whatever. But how tide was generated? The generating function of tide is very simple. Yeah. Sun, the attraction of sun, the attraction of moon. Yeah, that's it. So physically, it's a simple thing. But when you reduce to tide elevation, it becomes highly nonlinear, especially our recording, for many reasons. Reason number one, even though tide is Laplace tide, you can solve Laplace equation for tide, but the boundary condition is never linear. Second, is tidal wave propagate in shallow water. And shallow water equation is never linear. And third, when we measure tide, we never measure in deep ocean. We measure in the coastal region. All the tidal stations are near harbor, at the entrance of harbor. And that deep water wave coming to the tidal station, that transformation is not linear. So as a result, our tidal record can never be linear. Yeah. And not many people believe me because of this tidal machine seems to be linear. And not only that, they have all these terms to prove. That by itself is an interesting problem, and we will discuss that in the future. So the EMD basis is adaptive, because each of that CJ that I got, intrinsic mode function, is derived, is based on the data and derived from the data. And now I have shown you that the data, the base is complete. In other words, I can add all the components back to the original data to a degree of accuracy that is allowable by the method, by the tool. And it's orthogonal. I proved that. It's convergent. I did not talk about the convergent, but I sort of show you that 12 components all you got. You don't get any more. Yeah. So convergence and uniqueness are proved mostly empirically. And in fact, all of this are proved empirically, because I don't have the basis a priori. In other words, before you give me data, I don't have a base. My base is defined after I've seen the data. The base is derived from the data and based on the data. Therefore, the bases are adaptive. It's totally adaptive to the particular data. You change 1 point, the base changed. That is the adaptive property of the data, of the method. So all of this need to be proved. But up until now, the proofs are all empirical. I hope one day we can prove it to be more theoretical, but I doubt it. Yeah. The reason that in the past the people can prove this a priori, like for example, if you give me sine cosine Fourier analysis, I can prove it's complete, I can prove it's convergent, I can prove it orthogonal, I can prove it unique. I can prove all that before I even started. So this data, this base is a good base. I can use it anywhere. But unfortunately, once you prove a base with such property, then when you apply to data, you are so rigid. Your hand and both hands were tied. The only thing you get is a bunch of Fourier coefficient. And that Fourier coefficient has only mathematical meaning and no physical meaning. Yeah. So if we do not establish the basis a priori, we can only prove this a posteriori. This is after the fact. Yeah. Now the important thing that we're going to teach in this course is the Fourier's view on nonlinear data. What do you mean by nonlinear data? I talk about that the nonlinear pendulum. Okay, the nonlinear pendulum has roughly this form. That is, we have a sharp crest and sharp trough. So in order to demonstrate this, I come up with various mathematical models. This mathematical model is very simple. Cosine omega t plus a small number times sine 2 omega t. In other words, my phase function is not constant. Not just omega t, but omega t plus some oscillator, some modulation. That modulation was able to make the crest sharper and trough sharper too. Yeah. And if we look at this function, we will see that x equal to cosine omega t plus epsilon sine 2 omega t. I can expand it out easily. Cosine omega cosine whatever minus sine omega sine whatever. Okay? And this term, again, I can expand out. Cosine x equal to what? Equals to 1 plus x cubed 3 factorial and so on and so forth. Yeah. So if I expand this cosine out and I expand the sine out, sine is first is the argument. So I have epsilon sine 2 omega. Now once I get this, sine omega sine 2 omega, I can write as omega and 3 omega. So I can successfully expand this out to be cosine omega, cosine 3 omega, cosine 6 omega, and so on and so forth. So this is the expansion of that function in Fourier terms. Yeah, this is exactly the Fourier expansion. If we use this up to infinity many terms, we will recover exact this. So that's why Fourier can think any function as a linear combination of sine and cosine. Yeah. So they use linear combination of sine and cosine and reduce any function. But in fact, the function itself is frequency modulated. The frequency modulation has the power of changing the waveform from a sine waveform to a totally arbitrary shape, to a different shape. So if I will use the Fourier approach, I will have sine omega, sine 3 omega, and sine 6 omega, and so on and so forth. You can keep on going. This is the Fourier-based method. Even though this is not a Fourier transformation, this is we can use Fourier transformation, use spectrogram. We will get sine omega, sine 2 omega, sine 3 omega. Now, for what Hilbert will give you, Hilbert will actually give you a sinusoidal function. Hilbert will say, listen, there's no constant frequency. The frequency keeps changing. How it change? It changes up and down, up and down. For each period, each frequency, each period I actually change twice. And that's exactly what the mathematical model says. But mathematically, this colorful wavelet and this single line all represent this same data exactly. This colorful background gives you harmonics, and this gives you the modulation. So mathematically they are equivalent, but physically they are not. Physically they say you have one wave, two waves, and infinite many waves. You add it together. And to me, no. To me, it means your frequency is wobbling, is modulating. Yeah. Which one is better? Physically, this is better. But mathematically, the Fourier is equal elegant. Yeah. But if you want to understand the physics, I think you ought to try to use this kind of thing. Now this is what we call the Fourier spectrum. It's a function of time, frequency, and energy represented by the color of the intensity. And if we integrate the time out, we get the marginal spectrum. Marginal spectrum is integrate this time out. We only plot frequency as function of frequency and energy, and we get this. So Fourier will give you energy here, energy here. This is primary wave, the third harmonics, the six frequency, primary harmonics, all the way to harmonics, almost no end. Wavelet will give you a smooth curve like what we have here. What Hilbert will give you? Hilbert will give you a frequency here, and the frequency wobble back and forth. And that back and forth wobble represent the frequency modulation. Yeah. And this is very, very important. And this is also in the future application is very important too. Any time the fundamental frequency becomes broadening, that means nonlinear. That means frequency, intra-wave frequency modulation. Yeah. And that is the same thing as the harmonic distortion. But why is this better than that? Why is Hilbert better than Fourier? Because in the nature, when you try to understand something, you do a Fourier spectrum, and all the harmonics that represent nonlinear are all in high frequency. But when you get to high frequency, typically you have more noise, and it's harder to extract the quantitative data. Now we come back to the pendula that we discussed at the beginning. Here, I use epsilon equal to -1. I use gamma equal to 0.1. So this is a force function of gamma cosine omega t. Okay, I start from 0 and I compute this with the initial condition given here. And what I get exactly sharp crest and sharp trough. Why is that? Because the pendula with epsilon equal to -1, the pendulum gets shorter and shorter toward the extreme position. So in the extreme position, I move much faster. And move much faster. In the near zero, I move more smoothly and slowly. This is a nonlinear pendulum. Okay, but here I use epsilon equal to -1, and that epsilon is very large, and it will never be able to do a small perturbation analysis. In fact, if I let this running, shortly after this 200 points, it becomes chaotic. In other words, it will go through this phase and then shift to another phase. It becomes a bifurcation condition. So I cut it off here. I analyze this. This side, even on this side, you see the amplitude are not all the same. They are up and downs and up and downs. So I decided to take this data and subject to the decomposition. What I got a system oscillation like this, sharp crest and sharp trough, like the function that I give you. And I also get another function. This other function is plus minus 0.1, which is exactly gamma cosine omega t. That's my forcing function. So with this data, I recover the forcing function. I recover the system response. And I also have another subharmonics, which is typically of a nonlinear system when it's driven hard. Yeah. So in one shot, I get all this information. And this information, when I plot it back into the Hilbert spectrum, I have the system oscillation wobbling up and down gives me intra-wave frequency modulation. That means a frequency change within one period. But this will never repeat itself. See, this coming up and down, up and down. why I have this up and down, that we can, and this is the forcing function, which is very steady, and this subharmonics, which is, again, moving a little bit. Now let's examine this up and down. This is the frequency up and down, up and down. This top, of course, corresponds to the crest. The crest locally frequency is low. And the trough, well, this is also very high frequency. Now, and this is low frequency near the center section. Yeah. So each wave has a high and low in between. But why is this higher than, for example, this? This frequency is higher than that particular wave. You look, this wave, compare this wave to that wave. You can, your eye can almost tell you that this wave is broader than that. In other words, the period is longer than this. So once this nonlinear system gets started working, the frequency is never constant anymore. The frequency will change from one period to another period, from time to time. It's never periodical. It will never repeat itself. This is the chaos. But Hilbert transformation can spot this change through this instantaneous frequency curve. Now if I say, well, use any other method, what do we got? We got this fundamental frequency, we get harmonics. Can you tell me which particular wave is faster, which particular wave is slower? You will never be able to tell from this. But not only that, in order for this to be exact, you need all the harmonics. You cannot stop with second harmonics. But with Hilbert transformation, you can stop at the frequency of 0.2. Let's cover everything. Let's cover the modulation. So the Hilbert representation is a much more economical way to represent the data. And it's also a much concise way to represent the data. And a more precise way to represent the data. Not only that, it will also give you the physical meaning. Yeah. And speech analysis. This is when I say hello. Yeah. I say hello. If I record it, it will look like hello. This my voice. Yeah, I recorded it in my office. I digitize it. It's this. This data, if I present it in a different way, I will show it to you. These two are Fourier. This is wavelet. This is Hilbert. They are different, obviously. Not only even this, they are different. The narrow band and the wide band. Why we use narrow band? Because we want to know the frequency. Yeah. You want to know the frequency well, you have to take a longer data. If you want to know, if you don't care about frequency, you want to know the time, so you can take a shorter data. This is 10024, 1024 data points. This is 64 data points. 64 data points give you time precisely, but frequency gets smeared. The fact that you cannot determine time and frequency to arbitrary position is called uncertainty principle. And uncertainty principle is the consequence of integral transformation. And Fourier is integral transform. So you cannot determine time and frequency both very accurately. Now you look at this. This is wavelet. A wavelet compared to these two looks much better. But then you compare this with the Hilbert, it's again different. What Hilbert will give you not only separate the different frequency band, but it also within each frequency has this intra-wave frequency modulation. And that means my voice, that when I say something, my voice is not linear. When it comes out of my vocal cord to the vocal chamber and eventually pronounce the sound, it goes through all kinds of modulations. And the process certainly is not linear. Yeah. So you can see a simple data, you can have all kinds of different ways to represent it. It's not just Fourier. It's not just wavelet. Wavelet, especially. A lot of people are still using wavelet. A lot of people love wavelet. Wavelet, I only choose one wavelet, typical wavelet. Yeah. There are many, many hundreds, if not thousands of wavelet. You can plot each different wavelet will give you different answers, different presentation, because the basis changed. Okay? Here is the Hilbert transformation. It gives you such detail that no other method can got. Yeah. So this is an example. These are examples. So I will stop here, then I will continue next week to finish the introduction. The way that I designed the instruction is for very smart people. The smart people, once they listen to instruction, they don't have to come back to the class. Yeah. They have the whole course. Yeah. So this introduction will take a little bit longer to finish. Yeah. Thank you very much. Bye-bye.
Thank you. Bye-bye.
Thank you. You have any question, by the way? I forgot to ask you.
Oh, yeah.
Oh, yeah. Okay. You have a question. Please.
Yeah. You mentioned about the patent of the NASA. Patent of the NASA, you mentioned.
Oh, yes, yes.
Patent. Yeah. So in that case, so if we want to use the happy Hilbert transform, so should I say something to the NASA or something?
No. It's good news and bad news. The good news is that you can use it whatever way you want. The patent only covers United States. It does not cover any other country. Okay? So you can use whichever way you want, especially for research. Okay. But the bad news is that don't try to make money. If you make money, you better limit the money making in your neighborhood. In other words, you can make money. For example, in your case, you can make money in Japan. We can make money in Taiwan. But if we try to export this technology to the United States, you'll be sued. Okay. The patent protection only cover United States. Now, because of that, once I left NASA, I come back here. I have posted the method on the web. You can download all the software you need to make all the computation, because we are not governed by the United States patent law. Okay?
Okay, thank you very much.
Sure.
Yeah.
Yeah. Other questions?
Can I have some small question?
Sir, yes.
At the beginning of your class today, you talked about the empirical mode decomposition. And to do that, we need to get the envelope that touch the maximus and minimus. And if, I don't know how, at the very beginning of the data and at the very end of the data,
yes,
you need to set a certain boundary condition to get a straight line. What kind of things you can we have to do?
I cannot explain everything in one course. This is the introduction. Your point is very well taken. We will get into that in the course, not in the introduction. Okay? We have ways to try to take care of the boundary. Yeah. So in the course, we will have a special lecture cover that section. If I cover everything in one lecture, then it's not possible. Okay? Thank you very much for your question. That's a very important one.
Thanks.
Sure. All right. Any more questions here?
Let's go back to your next observation.
Yeah.
The third IMF.
Yeah. The third IMF. Well, you say this one or you want this one? This one.
say that there are also monotonic cycle and 19-year lunar year and solar year cycle. But why those cycles separate? Because that mode is half mass.
Yes. That's modulated by the sun.
But different time scale it should be appear in the other.
Each component actually has two informations. The first information is frequency. The other information is amplitude. This is all the frequency are AM and FM. Yeah. The modulation actually contains in AM here, not FM. Frequency is a carrier. So each frequency, that's one thing we have to be careful. In other words, each frequency, each component, we have FM and AM. Most of the time we are emphasizing FM. We sort of neglect the AM. The AM is equally important. Yeah, we'll touch that. Yeah. Okay? Yes.
Much earlier.
Yes. Let's.
You also explain the M1, R1. I don't know. I probably know what the M1 and R1 means, but what's the M1?
M1 is the mean, the first mean, the second mean. Each time I have a mean. Each mean is different. Right? Mean of the envelopes. Yeah. Each iteration, I generate a mean. That means in each iteration is different. Right? So we'll get back to that. This introduction is very rough, very much simpler. The reason is that I try to make it look simple so that you won't run away. Once you decide to stay, then I will give you the details. The devil is in the details. Okay. All right. Thank you very much. Bye-bye.
Bye-bye. Thank
you. Bye-bye.
Thank you.
Bye-bye. Okay. The course is over. If you have any question now, you can ask. We'll turn off the microphone.
切るよ。